Okay, this is page 18 of the scheduling notes. This is section 6.2 and it is fixed priority preemptive, or FPP for short, scheduling. And the text reference is 7.4.5. So the priorities are fixed. Another way to say this is that they are static priorities. And I want to emphasize this because the next scheduler that we'll cover is EDF, preemptive EDF, which has dynamic priorities. So they're static, and if you recall before I told you what static means, it means that they are assigned at compile time. If something is static, it happens at compile time. In this case, the priority is determined at compile time. And so what you do, or what the scheduler will do, is run the highest priority ready tasks in round robin fashion. So the first thing to note is that this is not a fair scheduling policy. There's no guarantee that a low priority task will ever get to run, but if that's the case, you've probably designed your application poorly, and you probably need a faster processor or more processors. So yeah, whatever. So say you have a set of 10 tasks. Probably not all of them will be ready at the same time. Some will be waiting on things like OS delay, the timer, waiting for an event to be signaled by an ISR, or waiting on other concurrency constructs like semaphores and mutexes that we're going to cover in the second half of the course. But of your ready tasks, ones that are not blocked, it'll choose whoever's got the highest priority, and we'll run that. If there's only one task at the highest priority level, it will just keep running that one task. If there's multiple, then it will cycle through them in round robin order, giving them each the same amount of time. So how would we implement something like this? It's going to be, actually the reason that I showed you the round robin scheduling is that the implementation for fixed priority preemptive is just a variation on that. So we're going to have a ready queue, but now we want to be able to rotate through tasks of the same priority level. So what we need is we need a ready queue for each priority level. So we are going to have an array of ready queues or ready lists, and we're going to have one per priority level. So let's look at an example to help you grasp this. Let's just say that we have 8 priority levels ranging from 0, which is the lowest, to 7, which is the highest. And Simsys RTOS v1 actually had 8 priority levels. With version 2 they went up to 34 priority levels, probably because some client requested it, though that's an awful lot of priority levels. There's not much that you can't do with 8 priority levels, I think. And let's just say in our scenario we have the idle task, and it has the lowest priority, so priority 0. And then let's say that we've got task 1 and task 2, and they have priority 2. And say tasks 3, 4, and 5 have priority 5. And let's just say that it's going to be one of T3, T4, T5 that's going to be running, assuming that these are all ready. So let's just add that. So say all in the ready state. So no task blocked. Our running pointer will point to one of T3, T4, T5. Let's make it T3. So that's an arbitrary choice, because it's just an example. And then we have our ready list. So our ready list will be an array of 8 pointers to queues, and actually they'd be pairs of pointers because they would be doubly linked. And so let's do the lowest priority at the top and go down. So this is the priority, and so priority 0 is the idle task, and it's the end of that list, so it's got a null pointer. Priority 1, there are no tasks in that queue. Priority 2, we have 2 tasks, so task 1 and task 2. And I'm not bothering with tail pointers, but I think you get the idea. And task 3, 4, priorities 3, 4, 6, and 7 are empty. Priority level 5, task 3 is running, so it's not going to be in the ready list because state is running, not ready. But we will have task 4 and task 5. And that's the end of that list. And so the question for you is, what happens when T3 finishes its time slice? We need to do a context switch to run another task. So let's do that on the next page.